In other words, the history of the universe is encoded in its present state, which may be surprising. In the early 1960s, there was a big debate on whether the universe had a beginning, a finite time ago. If so, the obvious question was, what happened before the beginning of the universe? As a joke, St. Augustine said, what was God doing before he made the universe? He was preparing hell for people who asked such questions. The alternative theory was that the universe had existed forever, as Aristotle believed, because something eternal was more perfect, and because that avoided awkward questions about the creation. In order to avoid the universe having a beginning at which physics broke down, Hoyle, Bondy, and Gould proposed the steady-state theory. In this, the universe would have existed forever, with new matter being continually created as the universe expanded, to keep the density constant. The steady-state theory was never in good agreement with observation, but the final nail in the coffin came with the discovery of a faint background of microwaves. These microwaves are the same as those in your microwave oven, but very much less powerful. They would heat your pizza only to -271.3 degrees centigrade, not much good for defrosting the pizza, let alone cooking it. You can actually observe these microwaves yourself. Set your analog TV to an empty channel. A few percent of the snow you see on the street will be caused by this background of microwaves. There was no way the steady-state theory could account for this background. The only reasonable interpretation of the background is that it is radiation left over from an early, very hot and dense state. As the universe expanded, the radiation would have cooled until it is just the faint remnant we observe today. The steady-state theory had a negative energy field, which is objectionable to particle physicists because it would lead to runaway production of pairs of positive and negative energy particles. Assuming all fields had positive energy density, Roger Penrose and I proved that if classical general relativity is correct, and certain physically reasonable conditions hold, the universe must have had a beginning at a singularity. A singularity is a place where the field equations of classical general relativity can be defined. So classical general relativity cannot predict how the universe should begin. This was the conclusion with which Pope John Paul was happy. At a conference on cosmology in the Vatican, the Pope told the delegates that it was okay to study the universe after it began, but they should not inquire into the beginning itself, because that was the moment of creation and the work of God. I was glad he didn't realize I had given the paper at the conference, suggesting how the universe began. I didn't fancy the thought of being handed over to the Inquisition, like Galileo. Many modern cosmologists are like John Paul. They are happy to apply the laws of physics that the universe after it began, but they are vague about the actual beginning. But unless one says what happens at the beginning of the universe, cosmology has no predictive power. All it can say is that things are as they are now, because they were as they were, shortly after the beginning. Although classical general relativity predicts that the beginning of the universe was a singularity at which the theory breaks down, we know that the theory has to be quantized, like the theories of all other physical fields. Although we don't yet have a complete theory of quantum gravity that is valid to all orders, we have an approximation which is good for practical purposes. This is based on Feynman's idea of the sum over histories. Richard Feynman was a colorful character who played the bongo drums in a strip joint in Pasadena and was a brilliant physicist at Caltech. He proposed that a system gone from a state A to a state B by every possible path or history. There will be a history in which the moon is made of blue cheese, but the amplitude is low, which is bad news for mice. Each path or history has a certain amplitude or intensity given by exponential s, where s is the action of the history, and the amplitude of the system going from A to B is given by adding of the amplitudes for each path. As I'm using the Euclidean approach with time imaginary, exponential s will be replaced by exponential minus s. Usually, the dominant contributions to the amplitude will come from histories close to a history that satisfies the classical field equations. The dominant contributions will then be the exponential of minus s, where s is the action of the solution of the classical field equations.